Okay, so let's take a look at this example. This is we're going to calculate a confidence interval for a mean where the population standard deviation is known. Exactly the situation that I told you that we're not going to run into very much in real life, but this is going to be our starting point. Okay, so first of all, sample size n is equal to 100. We took a sample of 100 people, produce a sample mean of 16. Okay, so I'm going to make believe this is my sample. This is not my population distribution now. This is my sample distribution. So the sample distribution, I would expect that's going to be 16, and I expect that's X bar. I would expect that to mirror the population's mean as well. Okay, and now this is the sample means now. So I want to put that up there so we don't confuse it with the population. Okay, so now what do I know about the standard deviation of this? Actually here, since it's a sample distribution, we're talking about standard error, not standard deviation. And the way we know standard deviation is standard error is equal to the standard deviation of population of the square root of the sample size. Well, happens that we know the standard deviation is 3. Okay, and the population, let's see, 100. Okay, so the population standard deviation is 3 over the square root of sample size, which is the square root of 100, is equal to 3 over 10, which is equal to 0.3. Okay, so now I say to myself, okay, fair enough. Standard error, the distribution here is 0.3. So I know that 95% of repeated samples should be between these two, within this range. I'm going to use that 95, I'm going to use that distribution, the standard error, I'm going to use it a different way this time. I'm going to use it as a tool to tell me how accurate my prediction based on my sample of 100 people, how accurate that prediction of 16 really is. One of the ways I can do that is I can tell you a probability that I'm correct. I could tell you a lot of. I could tell you one in. I think I'm. I think I got it almost on the head. I think I'm off by less than 5%. There's a lot of ways I could phrase that. As statisticians, the way that we describe the level of uncertainty about what the real population mean is. See, even though we calculated X bar from that sample of 100 students, 100 people, we really want to know what the mean of the population is. And we'll never know that. We'll never know that for sure unless we do the entire population. But we need to know, well, I found that the mean of 100 people was 16, and 100 people is a big sample, was 16, right? So how do I describe how certain I am about that number? Well, as statisticians, what we do is we establish a range. And that range that tells us or predicts for us that the true mean, the true population mean, is, while we think it's close to 16, we can say with a certain level of certainty that it's between these two numbers, above and below the number that I found for my sample distribution. Well, we know that there's a lot of different intervals like this, or confidence intervals. This is how confident we are that the true mean is between these two numbers within this range. I could say I want to be 90% confident. I could say I want to be 95% confident. I could say I want to be 99% confident. For the moment, I'm going to say I want to be 95% confident. That means 95% of this normal distribution. And we know usually that's 2 standard deviations above to 2 standard deviations below. So if I get a mean of 16, well, I can say that I'm 95% sure the real population mean is is 16 minus this distance here, 2 standard deviations. 2 standard deviations, that's 2 times 0.3, right? So that would be 0.6, right? 16 minus 0.6 is going to be 15.4. So this is going to be 15.4. And on the other end, with 2 standard deviations above, so we're going to take that 2 times 0.3, we're going to add it to the 16, and that's going to be 16.6. So in this case, I can say I'm 95% certain or confident that the real population mean is between 15.4 and 16.6. Okay, so now that's very nice for 95%. What do I do for 90%? Well, this is 95%, so this area here had to be 2.5 because these are always symmetrical, these normal distributions, right? And really, I knew by convention, you remember that we discussed this early in class, I knew by convention that approximately 2 standard deviations above, 2 standard deviations above the normal distribution represent 95% of the area under this curve, or probability, or number of people, and so on and so forth. And that came from the z-table. Well, if I want to be more confident that I captured the real amount, the real range for the mean, or the actual mean, if I want to be more confident, well, I'm going to move these sticks further out, right? Because I want to move those sticks further out, because then I have a wider net to grab the mean. So I'm more confident that I'm going to get this right. So that's a 99% confidence interval. For a 99% confidence interval, this area has to be half of 1%, and this area has to be half of 1%, right? Because only 1% can be outside of that range, right? So that I know is, but it's not an even number, right? It's going to be actually, I believe, 2.58 standard deviations away from the mean. So 2.58 standard deviations, I take that 2.58, multiply it by 3, and I would say, well, gee, I'm going to use 2.5 for the moment, just to make things simpler. That's 2.58 times 0.3 is going to be, let's see, 0.75. Let's see, 0.75, and and then it's going to be same thing, added and subtracted from 16. So this is going to be 15.25 to 16.75. So now I have a wider range for my 99% confidence interval. If I want 90%, right, I'm willing to, have more of a chance. I'm going to get to that in a second, Nicole. You're getting ahead of me, but you're absolutely right. If I want 90% confidence, I'm willing to take more of a chance that I'm wrong, so I can make the posts narrower, right? So 90%, that would mean 5% outside, 5% here, for 10% outside. And that would be, I believe, that would be 1.64 would be the number of standard deviations above and below. So we'd multiply 0.3 times 1.64 to get the number that we would have to add and subtract from 16. Well, now, the number 2 really was based on our experience, that's a good estimate for that 95% confidence interval. The real number is 1.96. So we know that instead of multiplying the 0.3 times 2, I would really multiply by 1.96 to do the same thing. We can have a formula for this to make it easier to remember. We're going to say that the confidence interval, whichever one it is going to be equal to x bar, right? Plus or minus, one time we're going to add it, one time we're going to subtract it. The z-score for the confidence interval, whatever it happens to be, this, a lot of times they'll put alpha and call alpha the level of error that we're willing to accept, right? So z times the standard error. Standard error happened to be 0.3 here. We calculated that from the population standard deviation of a square root of sample size. So for our 95% confidence interval, this would be 16 plus or minus 1.96 for a 95% confidence interval times 0.3 times, that's a times 0.3. And we just resolve that. And it would come out to approximately 15.4 to 16.6. Okay, but then you would actually use that number and get the right answer, right? And this is how we calculate a confidence interval. What do we need to calculate this confidence interval using these z-scores? The z-score 1.96 for 95%, or 2.58 for 99%, or 1.64 for 90%. What do we have to know in order to do that? We have to know the population standard deviation, because that gives us the confidence, sigma, exactly right. That gives us the confidence to say we know this distribution well enough to make that assumption that we can use these standard deviations to give us the range of values that we can capture, that we know that with that level of certainty we've captured the mean. Okay, so again, let's see how we did.